hear me over the headset? Okay, it works? Okay, great. So we'll do that. Yeah, and the 15 oscilloscopes, it might even have been 20. If you come into a lab, it has analog oscilloscopes, and they may have been on for quite some time. Don't try to save power by turning them all off. Next morning, people had been carrying oscilloscopes for 2 hours. So nonetheless, they kept me, so here I am. And I'm going to tell you a little bit today about the design of scalable quantum computing systems, and this is going to be part 1. So Alex Grimm here is going to give you part 2, and we're covering 2 technologies. So one is trapped ions, that's what I'll be speaking about, and superconducting circuits. Alex Grimm has a really nice recipe. You see PSI here, that's our newest shot. So we always have these drone shots of the campus because it's quite a large facility. But before I tell you a little bit more about PSI, I have this slide here just as a quick summary. I was already said where I am. I'm also affiliated with ETH Zurich, where I work at the ETH Quantum Center and handle external partnerships. And I still have grants and some folks in Sydney who are doing quantum chemistry research, so it's analog quantum chemistry. So many hats, quite useful sometimes, mostly very annoying because you have to change them in time zones. But in terms of the research areas, I also, as you can see, have worked in pretty much what you can do in this field. There's a little bit even on quantum sensing, and quantum chemistry was something that I've really spent quite some time on. So 2014, I think, or 13 even was when I started on this. It was a longer trajectory. And you've seen really nice highlight papers come out. Nature Cover, who's even among those. And in 2018, my paper came out as well. So when you commit to collaboration with someone and you're working out the problem, make sure you can actually carry it out. And I'm not in some pipeline. So that's just a word of advice when you have something really promising. Last 5 years, as was mentioned in Australia, I focused on optimal quantum control and quantum error correction. That was part of the so-called Logic Q program that I'll also speak about. And that's roughly, in a nutshell, what I've worked on. Where I am now is the Power-Share Institute, and this time you see it the other way around, which is important because you can see there's snow-covered Alps in the background. So I actually prefer this. And PSI is a large-scale facility. It's a national lab. It's got many large-scale facilities. You can see its light source. That's a synchrotron. We've got a muon source, neutron source, and a free electron laser over there. And that's not all that we do. Of course, also high-precision particle physics, proton radius. That question was raised here, that it's smaller, was discovered here for the first time. And there's more. There's proton therapy. So when you have an accelerator, you can also use it to irradiate tumors. That's what proton therapy does. Radiopharmacy is part of that too. There's some energy systems integration and a hot lab, because we've had a nuclear energy solution that produces some waste, so you need to deal with radioactive wastes. Also happens here. And the newest facility is that's the Quantum Computing Hub, which is a joint initiative between ETH Zurich and PSI. And so that's where I work, right by the river, so excellent real estate. A little bit humid at times, but otherwise really nice. We do have very strong connections, obviously, to ETH Zurich and to EPFL, as the Power-Share Institute is part of the ETH domain, which is this umbrella organization, if you will, of federal institutes. And there's the 2 universities, and then there are larger research institutes, and PSI is the largest one of these. But that was just a brief intro on PSI in the background. What I'm here for today is actually to talk about something else. It's to talk about this. Is quantum computing ready to scale? So where are we today? Is this a near-term reality, the blinking lights? Depends on which control system you buy. You can get blinking lights. But I also would like to emphasize what quantum computing is not. And this is just more of a fun fact slide, because I do give talks at various places, at companies at times, and they all have misconceptions. And so this is something, it's a bit aside from the scaling question, but probably most of you know this, but it's not faster. If you look at the clock rates, an ion trap, the state-of-the-art system, 10 to 100 hertz, maybe, when you run an algorithm. Superconducting qubits, there should be a star there. I think this was mentioned by Christopher earlier. Google's experiment had a little bottleneck, which is actually, if you look in the footnotes, quite a big one. Readout took quite some time. But if you take the fast Google gates, and then you go to Andreas Varos, Christopher Eichler's group at ETH Zurich, and you take their readout, which is the fastest in the world, and you combine them, you get to 377 kilohertz. Then there's latency. So is a quantum computer faster? Not really. It's not a parallel computer, one bit string at a time, right? Quantum mechanics, we need to do statistics, we need to ask the question multiple times, and you only get one answer. No matter how many paths of your problem or something you encoded in the quantum magic, one answer per shot. So it's not a parallel computer, and clearly not a replacement for classical computers. Nonetheless, high-performance computing data centers these days, they really love to have a quantum computer next to them, and their argument is, oh, it's big data. You need, for the quantum computer, a high-performance supercomputer. Well, you see down there 20 qubits, 10,000 executions. That's the amount of data. If you were around when modems were there, when you had the beeping sounds to connect to the internet, you could transfer this and also maybe write it on notepads and print it off. Not huge data. But coming back to the actual topic, where are we? So where are we is a good question to ask when you have commercial players in the market. Here are 4 roadmaps of, I would say, leading companies in this space. Honeywell, now called Continuum, and then you've got Google on the top right, IBM bottom right, and IonQ on the lower left. And what you see here is something that is partially a bit nuanced, and partially what you see in most of these roadmaps. And so in particular, there should be a laser pointer coming up, and I see it not come up. Ah, okay, there we go. Here it is, finally. Aha. So if you look at this here, the red is maybe not the best. 2020, where they started, and then there's 2030 for fault-tolerant quantum computing. You go to Google, that's their famous paper, 2019. Then there's a whole bunch of, that really looks like cascading and scaling, but no years are given, but physics are de-risked. And then 2029, they promise the error-corrected quantum computer. IBM is a bit more classical in the sense that they follow these roadmaps that you find from, say, Intel and others, where you give specific years and some metrics, a number of qubits. So it's all about scaling, as you can see, or not really see with the bad light. And for the ion trap quantum computing, it's about integration, it seems, and the same also for Honeywell up there, making things smaller, integrating these devices. So there's a clear roadmap, and these should be around the corner, right? If you look at that, it's pretty close. And in fact, this is for those who are not familiar with it. This is what was called, the proof. They called it quantum supremacy back then, the proof of a quantum advantage. So this is supposed to show you can do something on a quantum device that's faster than you could do it on any classical computer. And so to just open this quite quickly, what you do here on the top, right? This is the circuit. This is basically a qubit, each crossed here, and you've got these tunable couplers in between, A, B, C, D, so they can be turned on and off to create interactions between them. Any square here is a single operation. 2 qubit operations are these lines, and then every line is a single qubit. You start with all zeros, then you do something that has to be random as possible, and you get a random string. Doesn't seem like a very difficult problem. And in fact, it isn't a very difficult problem, but it is one that can take a substantial amount of time if you try to simulate it. And so with 53 qubits and just 20 steps of this circuit here, that took 200 seconds on the Google device. And their claim was the Summit supercomputer would take 10,000 years to do the same thing. Well, IBM, 1 or 2 weeks later, press release, no, if you do it right, big hardware, lots of hard drives, 2.5 days. Nonetheless, 200 seconds is still faster. And in the meantime, a Chinese group has also done this on an even larger chip. They confirmed that too. It takes 300 seconds, it's a bit larger, and again, days. So this is a real proof that a quantum device can be faster than a classical computer. And it's one that even software architecture are happy with. That was the main issue. And that main issue is also here. That's a physics example from 2017 where you could do the same claim. What we're looking for here is a phase transition. So you see a register of trapped ions on the left. And then, as always in physics, we like to do phase transitions. So things change. The magnet turns into a non-magnet at some temperature. So we're looking for kinks. And if you increase the number of spins here, then you can see this becomes clearer and clearer. That's at 16. And now we're at 53. And there's no exact calculation possible. Well, the only problem, and that is what this example shares with the one preceding it, there's no application, or people don't care about it. So quantum computing that Google showed, no practical application, maybe random number generation, but you can do this much cheaper. and much simpler. And here it's a physics problem that, well, physicists care about, and no one in commercial environments would even think about this. Nonetheless, what you see very often is obviously scaling. And I love that slide because I call it numbers game. And my favorite aspect is that the CEO of Intel at the time, Brian Kazanich, holds up this chip, which, if you worked in the lab, you know that these are SMA connectors. Whether there's any qubit is even, who knows? But he held it up in 2018. The future is coming. Look how we've been scaling. IBM, really commendable, has put up an online experience so people can use these chips. 50 and 20 qubit devices are available. And then the next one that was announced in 2019 was a 50 qubit device. Google, in parallel, had 9 excellent qubits. That was still John Martinez's group at UCSB. Then they worked on this chip, Bristlecone. Some of you might remember, 72 qubits. Never heard from again. Next thing you hear, 53 qubits. Well, it's actually a 54 qubit chip, but one wasn't connected. So it wasn't not working, it was just simply not connected. So 53, well, IBM corrects the press release 53. And now they have a 128 qubit or 127 qubit chip that they announced. And what I really want to illustrate here is everyone is talking numbers of qubits. But what does really matter? I'll give you an example at the bottom. That's my own work in 2011. I had 51 calcium ions trapped there. And I called them calcium ions. But only 20 of them were qubits. And those are the middle 20 marked there. Because those are the ones that I could actually control. You can have as many qubits as you want. If their coherence is not the same, if you can't control them, and if you can't connect them, that's the key thing. If you cannot connect them all with respect to one another, or there's some overhead with regards to that, then it doesn't matter how many qubits you have, because they need to work in synchrony. And so where are we? Well, I like to take this, I always draw this parallel between the good old analog days, so that's the ENIAC over there, and today's scaling, obviously, where we see plenty of transistors. The number of transistors increases all the time, and the quantum computing technologies, of which there are many, trapped ions, neutral atoms, superconducting loops, whichever way you prefer, they have all one thing in common: we're here. We're not even at the transistor yet, and this is one thing that always gets swept under the rug. When you have a transistor, you have digital logic. Digital logic is really cool because it's intrinsically error-corrected. You've got a 0, you've got a 1, 0 volts, 5 volts. It doesn't matter whether it's 4.3, 5.2. It's around about 5, so it's a 1. So you can live with errors. You can live with analog noise because you have this intrinsically stabilized 2-level system, a digital system, zeros and ones. Whereas quantum computing, well, is analog. And actually, if you look at the top left picture, some of the labs and some of yours might even look like this, right? Lots of wires, lots of cables, very analog. And there is a way around this. It's to digitize things so you can correct for errors. But quantum mechanics is tricky, and I'm not going to reach into the quantum error correction topic or the fault tolerance topic on Friday, where they will tell you all about this. But it's not a simple thing to correct these errors. Nonetheless, where we are is we're really in two separate tracks where we are in quantum computing. One is on this left-hand side, this noisy intermediate scale, or NISQ, as John Pascal loves to call it, and everyone likes to use the term, era where it's really you take a quantum device that you have, and you find a problem that you might have a solution for, or you have a solution and you're looking for the problem. But you do this without error correction with current-day hardware. The real hard path is on the right, and that's actually what I would love to talk about today. So really what we're doing here is what classical computing has done as well. It's abstraction layers. It's talking about the physical layer at the bottom, going to virtual layers, and all the way up to what I call the application layer there, or they call in the paper the application layer, which is what many of your startup companies today will offer you. Solving a quantum problem, here's my programming language, and here's how it will work on the machine that doesn't exist yet. So the beauty here in this quantum space is we know the stack, so we can approach it from both ends. We can start from the bottom and the top. And the key thing is this thing in the middle, quantum error correction. That's what we really need to make the magic happen. What I'd love to do today is just to give you an impression of the hardware side and a little bit about the control. This is a virtual layer. That's basically optimal quantum control. And I'll just briefly allude to quantum error correction in practice, but I'll leave this, defer this to the experts. And it's going to be a little bit of a tour de force. because there are many apps. So what I like to do is I like to go through this as quickly as I can, but if there are any questions along the way, please shout. Please interrupt me anytime. I hope we still have some more time at the end. But yeah, please jump in right away if you have any questions. So to get started, just a quick reminder of what trapped ion computers look like, quantum computers. This is the first quantum byte picture that Innsbruck in 2005. We improved the camera a little bit after I was not kicked out. So that's what it looked like then. And just as a reminder, the action movie Quantum Computing in Action, every time it's bright, it's a 1. Every time it's dark, it's a 0. So we do our shots repeatedly, turn the images to a bit string, do this many a times, do statistics, and thereby obtain the answer. And with trapped ions, we need laser beams to manipulate these qubits, which live in the structure, which is an ion trap, where they really line up nicely as a string. And in terms of ion traps, they've not been developed for quantum computing. They're actually made for mass spectrometry. So Wolfgang Paul got the Nobel Prize for this. You can see it's also 4 rods there. That's what meets you at the airport every time you get swiped for explosives. It's a mass spectrometer. But if you plug the ends, there's your ion trap. And I think Joe Goodwin probably told you a lot more about this. But I want to convey in this slide is there are many ways to make an ion trap. And the earliest ones were probably this ring trap, just 2 electrodes hand bent and put into a vacuum system. You can trap ions in the middle. The blade trap design that originated in Innsbruck around 2000 has then been since refined, and so this is one with the sapphire holder. But they're all basically following this design idea of having 4 electrodes and the ends are plugged. And that's one way to scale up. No, not one way to scale up. I will tell you more about the scaling later, but that's what these devices look like. But of course, that's just the core of the device. That's what it looks like in real life. Of course, it's always lit like this. So blue and all that. But basically, it's lasers. Lots of lasers, lots of electronics, and computers to control everything. And the actual device that I've just shown you actually lives over there in this corner. And when you look inside, you see the ion trap sitting here. It's 4.5 millimeters between these end caps. And then you can trap a string of ions in there, which is just 100 microns. But it's a 1D chain of ions, where each dot or each ion is a qubit. Now, that was the big lab scale. These days, you can actually buy the device in 2 19-inch racks. So people have really put some effort into squeezing this. And now this is commercially available, and also is supposed to give you an idea of how big these devices are, so you can hold them in your hand. And again, you see the same kind of device here. What's nice about this system is it runs at room temperature, because with ion traps you do the cooling via lasers, so you can work at room temperature. But if you really want to scale, you have to go this way. You have to do it with surface traps, with ion traps that really are made in a foundry, in a process. So 2008, we used the old, I think 486, so old Intel CPGA carriers. Then this is what a modern day thing looks like. You'll see this on every IonQ publication. And one thing you also do is you use cryostats, but for us it's not about temperature with ion traps, it's about better vacuum. I would say because we like to work dirty, not really, but because we like to use components that are not necessarily vacuum compatible. And if you've got good vacuum, you're really in business. So in ion traps we also put things in cryostats. And they look like this, and here's just a €2 coin for size comparison. That's an ion trap chip, which would be an array like that. So that's one idea of scaling to make these first on those devices. But then, of course, also this has a limitation, right? There's some macroscopic aspect to this. You can't really scale this up to hundreds, to thousands, to millions. So the approach for scaling, there are actually 2 approaches. One of them is to use, to follow Peter and Ignacio's idea from 2000, which was in Nature back then. You build a quantum hard drive where you have just ions trapped like this, and then the head moves around and reads these ions. It was a very nice conceptual idea, completely impractical, but it's a very nice idea. Not anything that anyone builds. But what was more close to reality then was on the right-hand side in 2000, where you have the surface then segmented. All these gold things here are electrodes, and then your ions are actually being shuttled around. So we're actually moving the information carrier on this architecture. And this architecture is now 20 years old, I only realize now. So that, but it has some overhead, right? You need these electrodes. And the alternative approach has been proposed by Chris Monroe and colleagues is to just use optics, to have these small ion trap modules like that, linear chains, and then you have one communication ion that is coupled to an optical fiber, and then you do interference experiments between modules. And so if 2 photons interfere here, and there's a click that you register, then 2 modules have become entangled. And you can then live with these linear chains, and you just have 1 ion that does the communication. So those are 2 approaches that are being pursued. I'm going to talk about only the top right one. And a nice concept there, I can actually show you by video. This is work by Karan Mehta, who was at ETH, but he did this originally when he did his PhD at MIT. And what we see here is basically how a unit cell of a surface ion trap would work that contains integrated optics. So let's have a look. And so you see the ion is hovering above the surface, and there are some electrodes, over here. And now light beams are coming out of the chip, brought there by waveguides that are underneath this electrode structure. You can see there are many waveguides. These are grating collimators, or grating couplers where the light emerges. Now you can think about an architecture like this, where the ions are shuttled, interact with one another, brought elsewhere, interact again, and then this could be one architecture, where the footnote is, well, we built a unit cell, and then it's all just about engineering. No problem, in air quotes. Obviously, it's not that easy, but a good breakthrough was done when actually Karan was at ETH. He was a postdoc in Jonathan Holmes' group. And what they've done is, and this is maybe a picture you might also have seen, they built this device here, where that's the ion trap chip. That's a fiber bundle that brings in the light. And here you can see a little bit the structure. So it's a multi-layer ion trap, but there's a photonic waveguide, a silicon nitride waveguide in there that allows you to bring the light in. And they were able to demonstrate a 99.3% fidelity 2-qubit gate. And this, it's close to the state of the art, but the important thing here is it's done on a surface ion trap, and the light is delivered from that trap. And that's really the big difference. Why, they may not be at the highest number. The highest fidelity is actually 99.9 something that you can get in trapped ions, but that's in one of these bulky traps. This is a completely different architecture, and it's now also there. And what you see here, again, this is now just a close-up picture, are these, maybe I'll use my mouse, that's probably faster. You still can't see it. Is there a way to turn down the lights up here? I guess not, right? It's all right, we'll deal with it. Perfect. Grating period here, so that's what these grating couplers look like. And if you want to know more about them, ask Gillen, who sits over there. He's our local resident expert. But basically, you bring your waveguide here, and that's for red light. So silicon nitride is great when you work with red light, but when it comes to blue light, which we need for laser cooling, it's a bit difficult, and we're working on new solutions right now to also bring in the blue light. The team at Lincoln Lab has shown this also to work, but it's quite tedious to talk to clean room and fabrication facilities to make this work. So that's one way of scaling. Of course, the other one, it's still a linear chain here, and now we just jump over here. This is the Honeywell device that you can see. There's part of this paper that they had, where it's a 1D chain, but here you can actually split these ions. You can split these chains and transport ions to left and right, do some operations there, bring them together, turn them around, and this way execute operations in separate regions. So that's the 1D version that was demonstrated. That's called the quantum CCD architecture, I should say. And that was one of the first demonstrations, but others have been shown at NIST beforehand. They just did this really well there. But the next step then is going to be, and this is also a NIST paper, to do this in multiple zones. So this is in fact what we do at the PSI Quantum Computing Hub. We're now looking at doing this in parallel trapping zones, because you can do it in a unit cell, and you can stay forever in the unit cell and do all the funny experiments in the unit cell, but you need to do scaling. And so that's really what our mission is. So this is about different processor zones and memory zones. You also would rather like to get rid of windows and external cameras. So one other thing you have to deal with is how to detect. And so again, this is Lincoln Lab on the left-hand side, integrating an APD, an avalanche photodiode, into these chips. There's also work by Sandia Labs on this, National Labs, but Lincoln has put ITO, which is a coating, a conductive coating on top, so they didn't suffer from some of the effects they saw here. But still, there's an active element very close to your ion, and an ion is a charged particle. right? And you have a charged particle detector that produces electrons in close proximity. Maybe not the best idea. Similarly, if you use a superconducting nanowire detector here, so it's a superconducting nanowire, it snakes around here. If a photon is absorbed, this thing goes normal conducting, and you can see a click, and the ion hovers just above it. But of course, there are radio frequency fields, so there's again some complication to it. And so one way that we're also thinking about is to use these grating couplers not just to outcouple light, but to also take it in waveguides and then bring it off chip or elsewhere where the detectors sit. That's the next thing that people are working on here. The other aspect was that, and that's a slide that I'm thankfully taken from John Chiaverini at Lincoln Lab, you have these ion traps, and again, that's one of those unit cells here, so this is where the ions live. There are many electrodes here, of course far fewer than you would have on a scalable ion trap, but still. The idea here, however, is that you program it using a serial port. So there are transistors or DACs here embedded in this chip, so you can see the layout here. So the electronics actually go onto the chip, are integrated with the chip, so you don't need the 550 million wires anymore that come out. I mean, if you look at any quantum computing experiment at scale these days, cable trees that big, and that's for 50 qubits. And going to 100 to 1,000 is, you need something like this. So with this brief going through the hardware, let me now come to the virtual layer. So this is a layer that was not necessarily very popular, but it's extremely powerful. And one observation that I'd like to start with here is that when you do randomized benchmarking, which is a technique that you can use to qualify gates to see what the error rates in these systems is, you get a plot that looks like this. And one thing that, I mean, nowadays people just publish the number that they get from this, but some still have the actual raw data. You get distributions like this. So this is the fidelity, you could say, on the top left. This is how, as a number of gates that you do on the x-axis, the more you do, the lower the state fidelity gets. So that gives you a proxy of the error rate. But you can see there's a distribution. And in fact, that distribution tells you a story. If you take a closer look, and this is something we did in Sydney, you can see, and we did this with engineered noise to really have control over what we're seeing. You can see that when you look at the variance of these distributions, if it stays narrow, it just gets narrower and narrower, then you have uncorrelated noise that just canceled and scales down as you go to many repetitions. If there's some noise correlation in your control signals, anything that conspires could be magnetic fields, could be amplitudes that fluctuate, but they do so in some way where they conspire, then you saturate and these distributions don't shrink. So even randomized benchmarking, which looks like a top-level benchmarking protocol, can give you an indication as to whether there's something hidden beneath that you might be able to deal with. And so doing this on larger scale systems, you might also need to do this, not brute force, but more intelligently. So we've also worked on a few things here where we assume a future array. So the top left is our future quantum computer, artist's impression. So we have the freedom to do whatever we like, but we say there are measurement qubits and there are other qubits that are available. And there's some noise fields here that we'd like to find out about, but we know that it's expensive to do calibration and measurements like this, so we want to do intelligent measurements, and that's what we've done in this paper. How can you learn about those noise fields in the least number of measurements? That's an entirely theoretical paper. There's one experimental aspect to it as well, so it works quite well. But it's just one of those ideas where when you go to scale, the questions change. It's no longer just about calibrating something, but it's about how do you do this quickly? How do you do this intelligently? Because you no longer have an infinite amount of time. And something else is there on the right-hand side. That's another example where we look at, and I'm not going to go into the details, this is noise on the ion trap, on the trapping potential that confines the ions. That noise can have many frequency bands, and if you find peaks like this, if you have means of finding those peaks, then that might tell you which component in your lab is responsible. So doing spectral analysis of these noise fields is very important. And the reason why that is important is because you can consult classical electrical engineering, and this is what's called the filter function framework. It's effectively the idea that if you know your noise spectrum, and you know that you do some operation, you can characterize that operation by what's called a filter function. And the filter function can be designed. That's like you design a low-pass filter or a high-pass filter. So you can take, if X is frequency space here, you can really design it in a way where it has some suppression at some frequencies and lets others pass. So this is like a pass band over here, but here's it's basically a high-pass filter in this case. And then the errors will also correspond because they are a convolution of the two. The noise that is present, your control that you engineer, and that might allow you to suppress errors. And in fact, it does allow you to suppress errors. And one of the most famous examples is how do you get rid of a pulse area error. So this is your amplitude is wrong or your pulse is a little bit too long. So you want to go from 0 to 1, but you didn't quite make it. So what you can use is you can use a composite sequence. So this is called dynamically corrected gates, or there are many names that this goes by. And this, in fact, is not invented for quantum computing. This is NMR. This is 70s. This is imaging. This is really, taking the old books and opening them and seeing what people have done to deal with errors in these other technologies. And so BB1 is one of those sequences. And you can see its effect here. There's overhead because you need to do more pulses, but then you actually get there. If this is a pi on 2 pulse that you wanted to do, you actually get to the equator in the end. And it doesn't matter that your pulse area was slightly off. But there's overhead. So with that, I want to also caveat, yes, there are ways around these errors, but they're not free. They come at a price. So you still want to make sure that you have the best possible qubit, and then you put these kind of corrections on top. Another example, so I'm just going to flash up briefly, is in a 10-qubit register, if you look at noise correlations across the system, so this is randomized benchmarking data. So you do lots of random gates, and then you look at how the fidelity decays. And if you don't just look at the decay, but you actually look at the correlations between qubits, how they perform, you can see there is some gradient in this system. And we actually here the problem is amplitude variations across the ion register. And so if you calibrate on the left-hand side ion, your other qubits will suffer. If you only calibrate on that guy, the others are not calibrated. And if you then use BB1, you can actually break those correlations. And if we look at the error rate, which is probably going to be more informative, you can see if we calibrate on the left-hand side ion, I'm still getting used to this new kind of pointer that's legal but very inconvenient. You can see the error per gate here. It's 10 to the minus 5 on that ion. That's great. But then you get this distribution here, which is because there's some underlying background noise field. But if you use BB1 gates, you can actually keep it very close, but you pay a price. Now your calibration qubit performs slightly worse, just due to the overhead. Nonetheless, if you have something that drifts, and this is now looking at, over time, just amplitude variations, effectively you do what you shouldn't do. You let the system just run and not feedback, not calibrate, not for drifts. Then you can see that this can be quite dramatic. This is the qubit basically is supposed to be at 0.5. If you calibrate it wrong, it goes to 0.6, but nonetheless, it stays at 0.6, whereas if you do it without calibration, it just drifts off. And again, here one of those corrective gates. There are companies now that sell you products that allow you to do this, and I think Andre gave a talk already on Monday, so Q-Control is one of those companies. One thing, and again, this is tour de force, something I'm not only going to name, there is modulation required. You don't just do square gates. You have to do phase modulation or amplitude modulation. And the only reason why I'm bringing up this slide here, that's 2-qubit gates, and ignore the things here in the middle. This is from that paper over here, if you want to know more details. I'm bringing this up because very often it is said that quantum gates and trapped ions are extremely slow, and other architectures are much faster. You can get high-fidelity gates at 1.6 microseconds if you use these techniques. So there's a way to get really fast gates, but, caveat again, 2 qubits, demonstration system, scaling, not proven. Nonetheless, it's quite impressive, and modulation was key here. The other thing is if you scale up to larger registers, and again here also, please ignore the images, but only look at this image here, you might need to do gates between certain pairs of ions, or maybe 3 ions, or 3 qubits at the same time. Now the question is, how do you do them? Because in these ions, you've probably heard of motional modes that we use to have these ions communicate with one another. That's motion. There are many frequencies, and if you have 20 ions, you have 40 radial motional modes. So there's a forest of frequencies that you don't want to talk to. You only want one. And to do this cleverly, you again modulate. and then you need to have a good strategy to do this. And again, a little bit of an advertisement here, but I may be forgiven, hopefully. One last comment on the hardware level. What's dominating the wall clock time? And this is a bit of it's a great paper, so don't get me wrong. This is a very impressive result that the Honeywell team has done there. If you start on the left-hand side, I really like that they draw up the circuit in this paper, and then they give you the budget. That's how much time it takes to initialize, then how much time it takes to move ions around, and then we eventually get to, and maybe it's better this way. I'll skip the pointer. You can see cooling. So the blue thing is cooling. That's basically just a measure. It's not computing. It's wasted time, if you will. If you then go to a quantum volume circuit, which is a benchmark that IBM proposed, and Honeywell is, I think, the only one really repeatedly implementing this because they just add an ion and get another order of magnitude. It's a super cool marketing tool if you're not IBM, because IBM is not really keeping up with that. Honeywell is really exploiting it heavily. But footnote, 6-qubit quantum volume circuit, when they run this, they spend the majority of time on cooling. So when you sum up all those times, you get to about a 7 hertz clock rate in this state-of-the-art system. So most of the things that we do here are laser cooling and not computing. So what we're currently doing, and pretty much many people in the field are doing, is looking at optimized cooling methods, other architectures where you could do sympathetic cooling. So you can have some qubits that do the cooling, laser cooling, whereas others do the computation. And there's a paper, which I find quite remarkable. So they got away calling it the OMG architecture. It's optical, metastable, and ground state qubits, but OMG. And that's the only one I think that's out there that has that acronym. David Wineland was on the author list, so don't get me wrong, it's a serious paper. But the idea here really is that you encode many different types of qubits in a single ion and then use that. So there's many ways of combining ions that we're still currently exploring to really help us with this overhead. With this, and I'm going to wrap up rather shortly, error correction, I'm not going to say much about this other than flipping up something or showing this slide and I think I'm running out of time, aren't I not? Okay, good. It's basically the idea is, again, to take many qubits, so the physical qubits, again, that are here on the line, and then you do operations on them, and then that string up correlations. So a nice way of depicting this is ignoring that's a linear chain. So again, here, geometries that you see for error correction, they don't have to be realized or mimicked in real life. You can have a linear chain do a 6-dimensional system, if you like. Here it's just 2, and we've got these, what are called plaquettes. So these qubits are grouped, and if an error occurs, by reading out what's called a syndrome, an error syndrome, you can find out which one of these 7 qubits has had an error. Very many subtleties to this, and you might need more than 7, but again, hint, hint, Friday will tell you more about this. Nonetheless, when you read out these syndromes, you would know how it works, and you get one of these graphs, and you want to be, this is the physical qubit error rate. This is how bad it would perform if you did nothing, and what you want to be on is you want to be on this slope. On the x-axis, we have the error, and here is your recovery probability or survival probability. So you want to be above that line. That's really what you have to show if you build a logical qubit. And once you have that, the story is simple. You simply scale. Right? You just put these things together. As easy as that. Well, not quite as easy as that, because it's really a long, windy road. So to get to fault-tolerant quantum computation is a bit of a challenge. And so you have to choose your qubit modality. You have to encode the quantum error correcting code. You have to read it out. And you have to, these things are just what various technologies have done, superconducting qubits and trapped ions. You have to read it out. Then you have to process it. And you can do that in post-processing. That's what most demonstrations. So if you read an error correction paper, all but one have not done full error correction because they've just done post-processing. So it's error detection, and then in post-processing, you throw away the errors and you see how it scales. I think, at least to my knowledge, there's only one paper that has done active feedback. That was Honeywell, again. And then you get to your logical qubit. So again, whether it was just by detection or whether you've actually done feedback, that's one thing. So now we're back at one logical qubit. Then you need 2 logical qubits. Problem, those 2 logical qubits need to talk to each other, and they don't. You have to do something called lattice surgery to make them talk to one another. And then when you actually master this level, you can scale up to a fault-tolerant computer. And just as finishing words, there was a program that ran for a long time, and I was part of that in Australia. Jonathan Holm at Zurich was part of this too. So we had a consortium, the Equal Consortium, which was one of 4 teams. There were 2 superconducting teams and 2 ion trap teams that were basically put against each other. And we had to perform. We're really called performers in these kind of programs. And the goal was to demonstrate one logical qubit. However you do it, however you want to play it, that was the goal. And now it's actually been done. So this program ran for a number of years, and success is achieved. So we've got a logical qubit now, 17 superconducting qubits. I think you've heard about this from Christopher earlier. 10 trapped ion qubits, and you get your one logical qubit. There's also another 17 trapped ion qubit experiments, so don't look too closely at those numbers. They're not yet meaningful at this level. But then you get one logical qubit, and 3 of the consortia have actually achieved this, and 2 of them had ETH contributions. The dark horse, as they usually say, was Honeywell, because they've actually implemented this color code and done the active feedback, and they were not this. But you know, everyone graduates, postdocs move on, that's history. But this is the success, so now we're back at 1, and if you remember the numbers game that I showed you earlier, we're starting back at 1, and then the next level is 2 logical qubits. What I haven't discussed, and I'm not going to do this in detail, is you need a software stack, you need dedicated hardware, you need fast readout electronics to make this happen, because we want low latency real-time feedback. You know, only an actively stabilized code will actually do a logical qubit, a useful logical qubit. And so, as last words, let me briefly say that there are alternative methods. There are different ways of trapping ions. The pole trap, and you've probably seen this in Joe Goodwin's talk, a pole trap and there's a penning trap. They look rather similar in these drawings, but one of them, the penning trap, has only a magnetic field and static electric fields, whereas the pole trap needs oscillating electric fields. Now, the penning trap, usually when people look at it, they think precision measurements, so doing this for quantum computing, maybe not so much. But then this is, again, Jonathan Holm's group at ETH. They came up with a proposal to make a microarray of penning traps, where each of these dots is an ion hovering above the surface. There are no oscillating IF fields in this. And then if you bring these ions closer to one another, they can interact. So maybe that's the way to go, because here, there's no RF field for trapping. But what you do when you, I think that gong is probably, okay. If you look at the frequencies, motional frequencies that these ions have, the key thing here is that even though there are many, you can see more than 250 in this system, there's some which are isolated that you could use to have ions talk to one another. So maybe this is a scalable hardware approach. The system has just trapped ions at ETH, so we're celebrating. And maybe that's the future to go, so no longer pole traps. Another way, and that's a bridge over to Alex's talk, bosonic codes. You may have heard about bosonic codes. Jonathan loves this picture, I hope. So there are 2 examples what you can do, and the main message, let me motivate from the bottom up, is 1 trapped ion qubit equals 1 logical qubit. If you don't do what I've just told you with this stack and error correction and gates and all that, but you actually use the oscillators, this motional degree of freedom to encode a qubit, looks like 3 superposed squeeze states. This is position and this is momentum. This is really talking about a quantum harmonic oscillator. And the qubit is only the transducer. The qubit is not what stores the information. Then you can create this. It's called a GKP code. Gottesman, Kitaev, Preskill, they came up with this idea. And you can use this thing, in fact, also, and this was recently published just this year, you can do quantum error correction. And I think the ETH team really got a very impressive increase in the logical performance. And that's 1 qubit for 1 logical qubit, completely different approach. That was trapped ions. Next, you'll hear about superconducting qubits, or how you can do it there. And with that, thank you very much. If there are any questions, happy to take.
Thank you, Cornelius. Well, thank you. We will be taking